Okay, can't see his face. Sorry. Okay, let's get this party started. Okay, so this is our second test, our second video rather, on 9.3, our test statistic. So as we look at that, I want to, first of all, let's talk about some calculator stuff. Now, previously or earlier today, we did some calculations to find the p-value if we were given the test statistic, meaning our handy-dandy calculator could not spit it out for us, so we had to find it, and we used the table. But I found out today, and this is through the help of JJ, shout out for JJ, that we could do this, and I thought it was an 84 only. So I decided, let me just see if it's an 83. Why could it not be an 83? And it's there. Okay, so how we can find the p-value in the calculator when we are given a test statistic. So take a moment to write this down. So go ahead and pause. Okay, welcome back. So let's do this in the calculator. Now, I'm going to do it for one-tailed, and when it's a two-tailed situation, I'm just going to multiply it by 2. The boundary thing does not seem to work. I know we were trying it earlier, and I'm sure we could figure it out, and I actually did figure it out, but it wasn't that serious. Just take it and multiply it by 2. So as I look at this problem right here, problem C, this is how I'm going to put this in the calculator. So I'm going to go to second vars, as I said, down to the T distribution CDF, press enter. Because I am looking at always, that table, remember, always is always positive. So for that reason, that's why I'm putting in 1.81. So what's going to go here is always my test statistic, then comma, some extreme value, comma, and then what did I ask for next? My degree of freedom. So you can see here that it gives me a p-value of 0.043. And what did we do when we found it on the chart? We just knew that it was less than 0.05. Now we are almost at a point of being ready to do a complete hypothesis test for a T test. So as I take you to the second one, okay, how do we use the calculator to conduct a significant test? To conduct a test, and I should say to conduct a complete test. Because here was to find the p-value given the test statistic. Here is when we have a complete one. So go ahead and write that down. And we're going to end up doing this all together tomorrow when we do number, I want to say 72, but I might be off on that number. But as you can see, what we're going to do is we're going to be going stat over the test, then go down, just down to number 2. And we're always going to have stat, well, maybe not, because tomorrow I think we're going to do one in which we have the raw data, which is a real pain because we have to do the look for the normal probability plot, etc., but we'll worry about that later. So you can see what goes in here is the mean and the x-bar and the standard deviation and your sample size, and then whatever your HA is what you highlight, and then you do the calculation. Now, the numbers I have in here are random numbers from who knows when, but I'll just show you if I utilize, and you can plug in these numbers, and I'm just going to go with the calculator. Okay, now look at this. I have a p-value. Well, look at my t. My t is 4.7. It's a huge t. And remember, when you have a big T, that means you're going to have a small p, which is confirmed right here. You've got a point, and you've got 5 zeros and a 1. So you know that you're going to reject the HO. And remember, this was just something generic that was in my calculator so you could see how it was done. Tomorrow we're going to do a specific problem. Speaking of which, we know the bottom line is that we cannot do things just with magic numbers. So as we slide down and see here, first of all, I need to change this. Okay, there we go. Okay, so here I'm still looking at the idea of, I'm not comparing the significant test and confidence interval, not at least yet. I just want to look at the difference between the T and the Z. So, because what we just did in the calculator, let's face it, if you just spit that out, that's considered magic numbers. Here is the formula, and as you look at the formula right here, it is what we've done before, but here we have the X bar, which is the sample minus the population divided by the sigma divided by the square root of n, which means here that sigma is known. But when sigma is unknown, we are using our T, and let's face it, we know this. What's the big difference here? The big difference is I'm replacing that sigma with the S because that's what I'm given. And the major difference is I've got a T and a Z in which I'm using two different charts. Also, please notice up here, I did write down my confidence intervals just as a reminder, which takes me to my next point. Is there a connection between a one-sided test and a two-sided test? And the answer is yes, it is. Because let's think about it. A confidence interval, let's look at a 90% confidence interval. Just generically chose that because it's a nice decadent number. Okay, if it's a 90% confidence interval, that means we have 5% on that end, another 5% on that end. Of course, that gives us 100% under the curve. Versus, as we look at, that is a versus, as we look at a left tail right here, that's 0.05. And if we look at a right tail right here, that's I hate when that happens. I don't know when it shut off. So, I'm so sorry, guys. Anyway, so as I was saying here, this is a one-sided test, and here we have the alpha to be 0.05, which of course, here I'm comparing that to the CI of 90. I'm not saying that the two of those, that if I have a 90% confidence interval, that means I have a 10% alpha. No. I'm comparing the two. So as I was saying here, if you have a CI of 90%, this is what your graph is going to look like. And if I have an alpha of 5%, it's going to either be here for the left tail or here for the right tail. But regardless, as you look at these two, the rejection region is in the pink. We're used to seeing this rejection region, but let's think about it. When it's a confidence interval, we haven't really thought about it as a rejection region. We've more so looked at this particular area right here as a support region. Okay, but here that's just a prime example, or let me do it correctly, failed to reject. That shows you with a picture how they really do compare. Now, as we continue the paired t-test, we're going to wait. That's going to be in the next video. Okay, it didn't sound like I was concluding, so we're going to wait for the paired t-test on the next video conclusion. So turn to page 18 of your notes and pause and read over it. Okay, welcome back. So what are they looking for right here? We are looking for our conditions and assumptions. So we're looking at our sins. Okay, we have a random sample of 50 students, or 50 children, sorry. Independence population of all children in Jordan is going to be greater than 10 times that sample size that we have right there. And here, thank goodness, we have a large count. So here we're going to assume normality because 50 is greater than 30. So much nicer than it was when we had to do our proportions. Okay, next, let's look at the next problem. Okay, now this is a two-tailed test. We have a n equals 25, which means we have a degree of freedom of 24. Like I said, they told us it was two-tailed, but not only that, we know it's two-tailed because of that. And remember, even though they give us a t value of a negative, we just take the absolute value because that's what our table shows us on the t distribution. They're all positive. Okay, so with that being said, let's do this in our two ways. Let's do it with our calculator. So in our calculator, you're going to be going again to first vars. No, second vars, I'm sorry. Going over to, let me do this again. I've got to do it at the same time I say it. Okay, I've got to go to second vars, go down to T CDF, which is, as I try to show both of them. So let me clear out. Let me clean this up. So second vars, down to T CDF, enter. Remember, we're always looking at the positive value. And the beauty of these, at least you know you're always, your boundary, your first boundary is always going to be the test statistic. So you have that. Okay, then comma, and then you have some extremely large number, comma, and then your degree of freedom. And that's where I got that 13, well, that 0.137. But, it's two-tailed. So all I'm going to do is multiply it by 2. So what some people do is they just literally, well, let me do this another way. They go 2 times that other number, and then it spits out the value. So let me insert that 2. So 2 times that CDF, because you know it's two-tailed. And you see you're going to get your answer of 27. Okay, too many brain cells for me. I just know take this and then multiply it by 2 a little later. Now remember, that's how we do it with the calculator. How do we do it with the table? Here, as we look at the table, we are finding our degree of freedom. We're going over to 1.12, or where we can see it. It is between two values, and then I slide up and find out that my probability value is between 0.15 and 0.10, but it's doubled, so that means it's between 20 and 30%, which our calculator confirmed that with it being 27%. The calculator is much more precise. And remember, I had to double it because it was two-tailed. Now, part D, this problem is a little bit backwards to me because part B asks what happens if it's less than. Oh, I need to finish answering the question for A. So as I look at A, the question was, what conclusion can you draw? What's a big p-value? So since it's a big p-value, I'm going to fail to reject in both situations, the HO. And since they didn't ask me for a specific conclusion of a specific scenario, I'm down with that. Now, as I was saying, to me, this was a little backwards because they say, well, what happens if it's less than? Okay, well, if it's less than, that means I didn't have to double my p-value. So that was the p-value I found originally. Okay, and I compared that one-tailed p-value to my alpha level. They want me to see what's happening at 0.05 and 0.01. Well, in both cases, again, I failed to reject. So those are the notes for today. I said okay, so on your quiz tomorrow, who knows what little weird things that I did might be on it. Are you feeling stressed? I don't know who Cal West is, but I need this. I need this. I'm squeezing, squeezing, squeezing. Ah! I'll see you guys tomorrow. Have fun. Bye-bye.